Hi there. I'd like to finish up our conversation we've had about derivatives so far by talking about the last step, multivariable derivatives. Unfortunately, we're not going to get to use single variable derivatives all the time. We're usually going to be dealing with multiple different variables that affect a problem. So anyways, let's talk about how we calculate derivatives of those functions. So anyways, like I was saying, most of the time in economics, we're going to deal with optimization problems that have at least two, if not more, variables. Anyways, that's going to be situations of consumer choice, it's going to be Cornell competition, many others. The list goes on. You're rarely going to see a situation with just one variable. Anyways, in these cases, we're going to need to make use of multivariable calculus to optimize those problems, specifically the technique known as partial derivatives. Now, don't get scared about these. They're actually very similar to single variable counterparts. I mean, the changes between a single variable derivative and a multivariable derivative are not complicated. The real trick that I teach my students is that just need to treat everything that is not being differentiated as a constant. So I'm going to show you situations. Think of anything that we're not calculating a derivative for as 3. Just pick a number. That's what number it's taking, and just let it stay as that number. So anyways, let's just jump right in and look at some examples. I want to show you this first example from consumer theory. So let's suppose a consumer could purchase two goods, X and Y, and they receive the following utility from their consumption. Their utility from consuming X and Y is equal to X to the 0.4 power times Y to the 0.6 power. So not only do I have two variables, but my exponents aren't even integers anymore. It'll make it a little bit more challenging. But this is similar to an actual utility function that you will use in your analysis. So first and foremost, let's calculate our marginal rate of substitution. Our marginal rate of substitution is going to be the negative marginal utility with respect to x divided by the marginal utility with respect to y. So just remember those numerators and denominators are both marginal utilities for goods x and y's. And as such, they are partial derivatives of the utility function for each variable. So we're going to need to calculate both of them in this case, one for x and one for y. So let's actually just jump right in. Let's start with good x and calculate a partial derivatives. So looking at this function, well, I have everything I need to calculate the derivative using the power rule. So since we're dealing with good x, we're going to treat good y as if it were just a constant. So again, think of y as just equal to 3 right now. How would this change if that were just the number 3? It really wouldn't. We just treat it normally and do the power rule. And you think about why we can do that. We're calculating a derivative with respect to x. So holding y constant makes sense here because we want to see how the utility changes only as we're varying the value of x. Anyways, let's go back to our power rule. First, we're going to multiply the coefficient by the exponent and then decrease the exponent by 1. And doing that is going to give us the marginal utility for x, which is just 0.4 times x to the negative 0.6 power times y to the 0.6 power. So I multiplied the utility function by 0.4, which was x's exponent, and then I decreased x's exponent by 1, which of course made it negative in this case. So like I was saying before, the y term is completely left alone. And that's just because it is technically a coefficient of x's term in this case. It is just a constant. It's a number and part of the same term as x. If there was a y that was off by itself in this expression, we would treat it like the derivative of a constant and delete it, or it'd be equal to 0 in this case. But because it's attached to an x, it's a coefficient of x, we leave it alone. All right. Now let's do the same thing for good y. And again, applying the power rule, we multiply it by 0.6, which is the exponent of y, bring it out front, and then we decrease the exponent of y by 1, which makes it equal to negative 0.4. But again, we completely leave the x term alone. It's treated as a constant, or a coefficient of y in this case, and left alone. If there was an x off by itself without a y attached to it, again, it'd be the derivative of a constant, and we'd get rid of it. So anyways, that gives me everything I need. I have the marginal utility with respect to x, the marginal utility with respect to y, and I can assemble those two expressions together into their marginal rate of substitution. So my negative marginal utility of x divided by the marginal utility of y is negative 0.4 times x to the negative 0.6 power times y to the 0.6 power. all of that divided by 0.6 times x to the 0.4 power y to the negative 0.4 power. Now, we can use some math techniques, which we'll talk about later, to actually simplify this by quite a bit. We can combine exponents, and this actually equals negative 2y over 3x. So I'll show you guys how to do this much simpler in the next unit. We can basically combine the exponents. So anyways, let's actually do one more application of multivariable derivatives, and let's actually look at an example of Cournot competition. So just as a reminder, Cournot competition is a situation where we have two or more firms competing as an oligopoly. We have a duopoly in this case, we have two firms, and they both set their quantities at the same time. So let's suppose that these two firms in this duopoly face a market demand curve of price equals 100 minus Q1 minus Q2. That's an inverse market demand curve, by the way, where Q1 and Q2 are firms 1 and 2's quantities, respectively. So basically, what we're going to find the market price is influenced by not only how much firm 1 decides to produce, but how much firm 2 decides to produce as well. So let's calculate the marginal revenue for firm 1. And just like before, we're going to calculate the marginal revenue by calculating a partial derivative of the total revenue function with respect to firm 1's quantity. So we're only going to be looking at firm 1's values. We're going to treat firm 2's as a constant. So anyways, remember that our total revenue function is just the price times the quantity. So, and again, we're going to use firm 1's quantity, and I can substitute in the inverse demand function for the price to obtain the total revenue for firm 1 as 100 minus Q1 minus Q2, all of that in parentheses, times Q1. And then to get the marginal revenue, I'm just going to take a partial derivative of that with respect to Q1. Now, I can use the product rule for that. So I have that my first function, g of Q1, Q2, remember it's got two arguments because it's got two variables, is 100 minus Q1 minus Q2, and h of Q1, Q2 is just Q1. I can calculate derivatives of that for both of them. I can use the power rule, and then I get that my derivative of g of Q1, Q2 with respect to Q1 is equal to negative 1, and my derivative of h of Q1, Q2 with respect to Q1 is 1. Now, a big thing to notice here is that with that partial derivative of g of Q1, Q2, it does not leave Q2 alone, because that Q2 is off by itself. It is not attached to a Q1 term. And like I said, we treat it as if it were a constant, and the derivative of a constant is equal to 0. So be very careful with that. We don't always leave it alone. We only leave it alone if it's actually attached to our variable of interest. So Q2 disappears from that derivative. Going back to our product rule definition, remember it's just the derivative of the first one times the second function plus the first function times the derivative of the second function. Well, plugging in all of our values, we have negative 1 times Q1 plus 100 minus Q1 minus Q2 in parentheses times 1, and all of that together equals 100 minus 2Q1 minus Q2. And that's going to give us the marginal revenue for firm 1. So what's neat is I could actually go through the same process for firm 2, and you are welcome to practice this. It would be very good practice. We'll obtain the marginal revenue function for firm 2 as 100 minus Q1 minus 2Q2. So we'll get a very symmetric answer in this case. So just going back and reviewing this a little bit, the general idea of a partial derivative is just to treat all variables except the one that we are differentiating with respect to as constant. So if they're attached to the other variables, treat them like a coefficient. If they're off on their own, treat them like a constant, and the derivative of a constant is equal to 0. So that's all we need to do to calculate multivariable derivatives. So that's actually it for our lesson on derivatives. Be sure to check out the walkthroughs for some additional practice. Thanks for watching.